It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to start off with rotational motion practice problems. So let's get started. Number one, we want to convert 90 degrees to radians. So we're just going to do a conversion factor. We'll start off with 90 degrees, make a set of parentheses, and we know that a circle is 360 degrees. We're going to put that on the bottom because we want to get rid of degrees. And there's 2 pi radians in a circle. So on the top, we're going to write 2 pi radians. And radians are units of measure, so we have to keep that in our answer. So if we work this out, we get pi over 2 radians. And if we simplify that in our calculator, that also equals 1.57 radians. Number 2, determine the angular displacement of a ladybug on a turntable as it rotates from 40 degrees to 100 degrees. So instead of finding the displacement or linear displacements, we're going to calculate how much it rotates. So the change in theta, that's the angular displacement, is going to be the final position, angular position, minus the initial position. So that would be 100 degrees minus 40 degrees, and that gives us 60 degrees. Oops. Notice that we get a positive answer because when we're talking about rotational motion, going counterclockwise is positive, and clockwise would be the negative direction. Now let's convert this to radians. So 60 degrees to radians. On the top, 2 pi radians over 360 degrees. That's going to give us pi over 3 radians. And again, in our calculators in decimal form, we get 1.05 radians. Letter 2a, we want to find its angular velocity after it's spinning around for 2 seconds when it goes from 40 degrees to 100 degrees. Our angular velocity omega is equal to the change in theta, the angular displacements, all over the time. That equals 1.05 radians over 2 seconds, which gives us 0.525 radians per second. So 525 radians per second. Number 3, calculate the angular velocity of Earth for 1 day. And we want to put that in seconds. So first of all, in 1 day, the change in the angular displacement for Earth, it rotates once, so that's just 2 pi radians. And we know the time it takes to go around in 1 day is 24 hours. But we want to put that in seconds. So there's 60 minutes in 1 hour. And then we go from minutes to seconds, 60 seconds per 1 minute. And that gives us 86,400 seconds. So to get the angular velocity omega, that's delta theta over t. Sorry for running out of space. That gives us 2 pi radians over 86,400 seconds. Plug and chug, and we get 7.03 times 10 to the negative 5, so really small number, radians per second. Number 4. Will is riding a unicycle. The unicycle accelerates from rest to an angular velocity of 15 RPMs. That's revolutions per minute in 6 seconds. We want to find the angular acceleration of the unicycle. That's going to be alpha. It starts from rest, so his initial angular velocity is 0 radians per second. His final angular velocity is 15 revolutions per minute. And we want to know what that is in radians per second. So let's go from minutes to seconds first. That's going to be 1 minute per 60 seconds. And then we want to go from revolutions, and we know that there's 2 pi radians, so 1 revolution is once around the circle. So we could go 2 pi radians per 1 revolution. And that'll give us a final angular velocity of 1.57 radians per second. The time is 6 seconds, and we want to find alpha, the angular acceleration. We know omega I, omega f, and t. We can use the formula alpha is a change in omega all over the time. That brings us to 1.57 radians per second minus 0 radians per second all over 6 seconds. Plug and chug, and we get 0.26 radians per second squared. Next problem, number 5. What is the linear velocity of Earth's equator for 1 day? So if you're standing at Earth's equator, what is its linear velocity? The time we know in seconds from before is 86,400 seconds. We can look up the radius of Earth at its equator. That's 6.37 times 10 to the 6th meters. We want to find what is its linear velocity. We know from the previous problem, we solved for omega, its angular velocity, and that was 7.3 times 10 to the negative 5 radians per second. And we also know its change in its angular displacements, or change in theta, that's 2 pi radians. What we're doing is we're going from its angular velocity to the linear velocity. The conversion for that is v equals omega r. So v equals 7.3 times 10 to the negative 5 radians per second times the radius, 6.37 times 10 to the 6th meters. That gives us a velocity at the equator to equal 465 meters per second. Next problem. You're watching The Lord of the Rings, The Fellowship of the Ring, extended edition, which is 4 hours long. What is the angular displacement of the hour hand as you watch the movie? We know that the time is 4 hours. And what we want to find first is the angular displacement, we say delta theta, for the hour hand. So for the hour hand for 4 hours, the hour hand is going to rotate 1/3 around the clock. 1/3 of a circle is 120 degrees. And all we want to do is convert that to radians. So we're just going to do 2 pi radians over 360 degrees. And that gives us a change of theta to equal 2.09 radians. Because the hour hand is going clockwise, it should technically be equal to negative 2.09 radians. We can also measure the angular displacements of the minute hand. Again, the time is still 4 hours, but this time the minute hand is going to rotate around 4 times to give us 4 hours. So that's 360 degrees times 4 times of rotations, which gives us 1440 degrees. And we want to put that in radians, so 2 pi radians all over 360 degrees. And for the minute hand, we get the change in theta to equal 25.17 radians. Number 7. The moon rotates on its axis in 27.3 days. We already have the conversion, 2.36 times 10 to the 6 seconds. Its radius is 1.74 times 10 to the negative 6 meters. 10 to the positive 6, sorry, meters. What is its linear speed of an astronaut on the moon's equator due to the moon's rotation? So again, we want to find v, the linear speed, which means we have to go from angular velocity to linear velocity based on the given information. The change in theta, its angular displacements, is equal to 2, let's put it over here. The change in theta for 1 day is equal to 2 pi radians. And we know that v, the linear velocity, is equal to r, the radius, times omega, the angular velocity, sorry. And we also know that omega is equal to the change in theta all over the time. So if we plug in change in theta over t for omega, that leaves us with v equals r delta theta all over the t. That gives us v equals 1.74 times 10 to the 6 meters times 2 pi radians all over the time, 2.36 times 10 to the 6th seconds. Plug and chug and we get a velocity of 4.63, linear velocity, of course 4.63 meters per second. Number 8. A carousel accelerates from rest to an angular velocity of 0.3 radians per second in 10 seconds. What is its angular acceleration? Omega I, the initial angular velocity, is 0 radians per second. Omega F, the final angular velocity, 0.3 radians per second. Time is 10 seconds. Alpha, the angular acceleration, is what we're trying to find. We look in our reference table. Alpha is equal to the change in omega all over the time. 0.3 radians per second minus 0 radians per second over 10 seconds gives us an angular acceleration of 0.03 radians per second squared. Letter B, what is the linear acceleration for a person at the outer edge of the carousel having a radius of 2.5 meters from the axis of rotation? We want to find A, the linear acceleration, so another conversion factor. A is equal to r times alpha. The linear acceleration is equal to 2.5 meters times 0.03 radians per second squared. Plug and chug, we get an acceleration of 0.075 meters per second squared. Number 9, a CD player was designed. I'm not sure if you know what CD players are nowadays. A CD player was designed to vary the disk's angular velocity so that the point being read by the laser moves at a linear velocity of 1.25 meters per second. So V, 1.25 meters per second. What is a CD's angular velocity, omega, when the laser is reading information on an inner portion of the disk at a radius of 0.03 meters? We're going from linear velocity to angular velocity. The conversion is V equals omega r. So omega equals V over r. That's 1.25 meters per second over 0.03 meters. That gives us an angular velocity of 41.7 radians per second. Letter A, or part 2. What is the angular velocity when the laser is reading the outermost portion of the disk, which is at 0.06 meters? Well, we know the object, if it's spinning around the disk on the innermost part and on the outermost part, they're both going to rotate 360 degrees, which means their angular velocity will be the same, because it takes the same amount of time to go from point A, from the beginning to the end, as it does on the innermost part as well as the outermost part. So omega, the angular velocity, stays the same, which is 41.7 radians per second. All right, last page. The outer edge of a truck tire has a radius of 45 centimeters, which is 0.45 meters, a linear velocity of 23 meters per second. What is the angular velocity of the tire in radians per second? Same thing, conversion factor, V equals R omega, which means omega equals V over R. Omega equals 23 meters per second over 0.45 meters. Plug and chug, and we get 51 radians per second. Okay, the next problems, 11, 12, and 13, all have to do with the force of gravity and the universal gravitational constants, which is what is the force of gravity acting between two objects. 11 and 12, we're going to use some proportional reasoning. We're told that Bryce weighs 700 newtons on planet Earth. What does Bryce weigh on planet X if planet X has the same mass as Earth, but 3 times larger? Let's look at the formula for the force of gravity between two objects. In this case, it's between Bryce and Earth. F sub g equals big G times m1, m2 over r squared. When Bryce goes from one planet to the next, the gravitational constant g is going to stay the same. The mass of Bryce stays the same. So what we're looking at is what is the relationship between the weight of Bryce when the mass of the planet or the distance between the center to the surface of the planet changes. So in this case, planet X has the same mass as Earth, which means we don't care about its mass because it doesn't affect the problem, but it's 3 times larger. So we could say Bryce's new weight, F sub g prime, is proportional to 1 over the distance between the center squared times whatever his old weight is. So Fg prime is proportional to 1 over, it's 3 times larger, gotta square it, times his original weight, which we could put as 700 newtons. Plug and chug, and we get Bryce's new weight is equal to 77.8 newtons on planet X. So when the planet's size increases but its mass stays the same, we can see that Bryce's weight is going to decrease by 1/9, 1 over 3 squared, of what it was on Earth. Talon weighs 600 newtons on planet Earth. What does Talon weigh on planet Y? If planet Y has the same radius, but twice the mass. Let's start with the original formula. F sub g equals g m1 m2 over r squared. Again, r isn't the radius, it's the distance between the centers of the objects. So when Talon goes from Earth to planet Y, g stays the same, Talon's mass stays the same, and we're told that the Earth and the planet Y are the same radius, so r stays the same. Which means Talon's new weight, Fg prime, is proportional to the mass of the new planet times whatever her original weight is. So Fg prime is going to equal 2, because the mass doubled, times 600 newtons, Talon's weight on Earth. That gives us 1200 newtons. So when Talon goes to a planet that's double the mass, Talon's weight is going to also double in this case, because Fg prime is proportional to the new mass of the mass of the new object. Last problem, then we're done. What is the force of gravitational attraction between the Earth and the Moon if the Earth has a mass of 6.0 times 10 to the 24th kilograms, the Moon has a mass of 7.4 times 10 to the 22, and the distance between the two is 4 times 10 to the 8th meters? This problem, we're just simply plugging and chugging. F sub g equals g m1 m2 over r squared. G is the gravitational constant. It's on the front page of your Regents reference table. That's 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. And that's times m1, which we could say is Earth, 6.0 times 10 to the 24th kilograms, times m2, the mass of the moon, 7.4 times 10 to the 22 kilograms. These numbers can also be found on the front page of your reference table. All over the distance between the centers, 4 times 10 to the 8th meters, and we have to square that distance. Plug and chug, and we get the force of gravity between the Earth and the Moon to equal 1.85 times 10 to the 20 newtons. That's it for this video. Thank you for watching. Hopefully you found it helpful, and I'll see you next time. See ya!